Imagine standing on a silent, serene night, gazing up at the countless stars that pepper the inky blackness. Each tiny pinprick of light represents a distant sun, potentially orbited by its own planets. Our Milky Way galaxy alone holds hundreds of billions of stars, and there are trillions of galaxies stretching out to the very edges of the observable universe. Given these incomprehensible numbers, it seems almost mathematically certain that life, in some form, should be thriving out there. Maybe not little green humanoids, but perhaps microbial mats or even vast, ancient civilizations that have mastered technologies we can only dream of. So here's the mind-bending question that keeps scientists and stargazers alike awake at night. If the universe is so incredibly vast, teeming with possibilities, why haven't we found any signs of alien life? Where is everyone? This profound silence, this cosmic enigma, is what we call the Fermi Paradox, and it's one of the most intriguing and humbling mysteries in all of science. The Fermi Paradox isn't just a quirky thought experiment. It's a fundamental challenge to our understanding of life, the universe, and our place within it. It forces us to confront the stark contradiction between the high probability of extraterrestrial intelligence existing and the complete lack of observational evidence for it. Think of it like a cosmic game of hide and seek, but on an unimaginable scale. We're the eager seeker, peering into every nook and cranny of the cosmos, listening for even the faintest whisper, yet we hear nothing. No radio signals, no megastructures orbiting distant stars, no probes visiting our solar system, just an overwhelming, deafening silence. This paradox isn't new. It was first famously posed by physicist Enrico Fermi decades ago during a casual lunch conversation, and ever since, it has sparked endless debate and speculation, pushing the boundaries of our scientific and philosophical inquiry. Today, we're going on an extraordinary journey to explore this very paradox. We'll delve into the many potential solutions, from the idea that life might be far rarer than we imagine, to the chilling possibility that advanced civilizations inevitably destroy themselves. We'll consider theories that suggest alien life is simply too far away or too different for us to detect, or perhaps they're deliberately avoiding contact with us for reasons beyond our comprehension. This isn't just about finding aliens, it's about understanding the fundamental conditions for life, the future of humanity, and the incredible, humbling scale of the cosmos. Prepare to have your perceptions challenged and your imagination ignited, because the answers to the Fermi Paradox might tell us more about ourselves and our destiny than we ever thought possible. Let's start with the very foundation of this cosmic mystery. What exactly is the Fermi Paradox? At its heart, it is a stark contradiction, a profound tension between two seemingly irrefutable ideas. On one side, we have the overwhelming statistical probability that the universe should be teeming with extraterrestrial civilizations. With billions of galaxies, each containing billions of stars, many with their own planetary systems, it feels almost inevitable that life, and even intelligent life, must have arisen elsewhere. Yet, on the other side of this paradox, we face a crushing, undeniable reality: the complete and utter lack of any observational evidence for such life. No alien signals, no artifacts, no proof whatsoever. This deafening silence in a seemingly crowded cosmos is the core of the Fermi Paradox. This isn't some new age musing. It's a concept rooted in a deceptively simple question first posed by the brilliant physicist Enrico Fermi. The year was 1950. During a casual lunch at Los Alamos National Laboratory, Fermi, along with colleagues Emil Konopinski, Edward Teller, and Herbert York, was discussing recent UFO sightings and the possibility of faster-than-light travel. As the conversation progressed, Fermi reportedly blurted out, "Where is everybody?" This seemingly innocuous question, delivered with characteristic insight, immediately highlighted the glaring discrepancy between the likelihood of alien civilizations and the absence of any contact. His colleagues instantly understood the weight of his words, recognizing the profound implications of that single, powerful query. Fermi's question wasn't just about little green men. It was a challenge to the very assumptions underlying our understanding of life's prevalence in the universe. It ignited a debate that continues to this day, spanning astrophysics, biology, philosophy, and even sociology. To fully grasp the magnitude of Fermi's question, we often turn to another foundational concept, the Drake equation. While not a definitive calculation, it serves as a powerful framework for estimating the number of active, communicative extraterrestrial civilizations in our Milky Way galaxy. Developed in 1961 by astronomer Frank Drake, this equation multiplies together a series of probabilities: the rate of star formation, the fraction of stars with planets, the average number of planets that can support life, the fraction of those planets where life actually arises, the fraction of life-bearing planets where intelligent life evolves, the fraction of intelligent civilizations that develop technology capable of interstellar communication, and finally, the length of time such civilizations release detectable signals into space. Each factor in the Drake equation carries immense uncertainty, yet even with conservative estimates, the initial results often suggested a vast number of potential civilizations. This numerical prediction, however, stands in stark contrast to the silence Fermi observed, fueling the paradox and making us wonder which variable in the equation we might be fundamentally misunderstanding. To truly understand why the Drake equation is so central to the Fermi paradox, we need to break it down piece by piece. Imagine it as a series of cosmic filters, each one narrowing down the possibilities until we arrive at a final, estimated number of intelligent civilizations. The equation begins with a factor called n, which represents the number of communicating civilizations in our Milky Way galaxy. This n is then determined by multiplying 7 distinct variables, each one a crucial step in the grand cosmic lottery. First, we have our star, the average rate of star formation in our galaxy. How many new suns are being born each year or decade or century? Scientists have a relatively good handle on this one, thanks to extensive astronomical observations. Currently, we estimate about 1 to 2 new stars are born in the Milky Way every year. This number, while seemingly small in the grand scheme, provides the raw material for everything that follows. Next is FP, the fraction of those stars that have planets. For a long time, we could only guess at this. Then, with the advent of exoplanet hunting missions like Kepler, we discovered that planets are incredibly common. It turns out that most, if not all, stars in our galaxy likely host at least one planet. This dramatically shifted our perspective, moving us from a universe where planets might be rare to one where they are the norm. This factor alone significantly boosts the potential for life. Following that is NE, the average number of planets per star that are capable of supporting life. This is where things start to get a bit more speculative. We're looking for planets that orbit within the habitable zone, often called the Goldilocks zone, where temperatures are just right for liquid water to exist on the surface. But habitable is a complex term. It includes factors like planetary mass, atmospheric composition, and even the stability of the star itself. Some estimates suggest that a significant fraction of planets, perhaps 1 in 5 or even more, could fall into this category. After NE, we encounter FL, the fraction of those habitable planets where life actually arises. This is a monumental question, one that touches upon the very origin of life itself. Is abiogenesis, the process by which life emerges from non-living matter, a common occurrence given the right conditions, or is it an incredibly rare fluke? We simply don't know. Some biologists believe that if the conditions are right, life is an almost inevitable outcome. Others argue it might be an extremely improbable event, a cosmic miracle that happened only once here on Earth. This variable introduces enormous uncertainty into the equation. Next, we have Fi, the fraction of planets with life where intelligent life evolves. Even if life is common, does it necessarily lead to intelligence? Earth's history suggests that while life has been present for billions of years, complex, intelligent life is a relatively recent development. Many evolutionary pathways don't lead to sapient beings. This factor hinges on whether intelligence is a predictable outcome of evolution or a rare evolutionary accident. Then comes Fc, the fraction of intelligent civilizations that develop technology capable of interstellar communication. This isn't just about being intelligent. It's about developing the scientific and technological capacity and the inclination to send signals out into the cosmos. A civilization might be intelligent but never develop radio technology, or perhaps they choose not to broadcast their presence. This adds another layer of unknown, as it depends on the motivations and technological paths of alien societies. Finally, the last and perhaps most crucial variable in the Drake equation is L, the length of time such civilizations release detectable signals into space. This is often referred to as the lifetime of a communicative civilization. If intelligent civilizations rise, build advanced technologies, and then quickly destroy themselves through war, environmental catastrophe, or some other self-inflicted wound, then L would be very short. If they learn to overcome these challenges and achieve long-term stability, L could span millions or even billions of years. This single factor can dramatically alter the final outcome of the equation. A short L would mean civilizations are constantly popping in and out of existence, making them hard to find, while a long L would mean many long-lived civilizations should be broadcasting across the galaxy right now. As you can see, each variable in the Drake equation carries its own set of uncertainties, ranging from relatively well-understood astronomical factors to highly speculative biological and sociological assumptions. Depending on the values you assign to these variables, the resulting estimate for n, the number of communicative civilizations in our galaxy, can vary wildly. Optimistic estimates, often made by those who believe life is relatively common, might suggest millions of civilizations. Pessimistic estimates, on the other hand, could conclude that we are effectively alone. This vast range of possibilities is precisely what fuels the Fermi paradox. If the optimistic estimates are correct, then the silence we observe is truly perplexing. If the pessimistic estimates are right, then the paradox dissolves, but it leaves us with an even more profound and perhaps lonely conclusion about our place in the universe. The Drake equation, in its elegant simplicity, lays bare the core tension of the Fermi paradox, showing us exactly where our assumptions about the universe's crowdedness might conflict with its apparent emptiness. Given the vast uncertainties within the Drake equation, how can we possibly reconcile the high probability of life with the deafening silence? This brings us to one of the most compelling and chilling proposed solutions to the Fermi paradox, the Great Filter hypothesis. The Great Filter suggests that at some point in the long evolutionary path from simple life to a flourishing, spacefaring civilization, there exists a formidable, almost insurmountable barrier. This barrier, or filter, is so incredibly difficult to overcome that it drastically reduces the number of civilizations capable of reaching a point where they can communicate across interstellar distances. Think of it as a cosmic bottleneck, a hurdle that most potential intelligent life forms simply cannot clear. This filter could be a single, incredibly difficult step, or it could be a series of very challenging steps that collectively form a near-impossible gauntlet. The critical question then becomes, where in the sequence of cosmic evolution does this great filter lie? The implications of its placement are profound, leading to two primary, very different, and equally unsettling possibilities. The first possibility, and perhaps the more comforting one for our present existence, is that the great filter is behind us. This means that the incredibly difficult step, the monumental challenge, has already been overcome by humanity, making us incredibly rare and perhaps even unique. If this is true, then the silence we observe isn't because other civilizations are out there but choosing to be quiet. It's because they never made it past the filter. Consider what steps could constitute a filter behind us. It could be the very origin of life itself, abiogenesis. As we discussed, the transition from non-living matter to the first self-replicating organisms might be an astronomically improbable event. Despite our best scientific efforts, we still haven't fully replicated abiogenesis in the lab. If the conditions required are so specific, so rare, that it only happens once in a trillion star systems, then Earth could be that one in a trillion. Another potential filter behind us could be the evolution of complex multicellular life from simple, single-celled organisms. For billions of years on Earth, life remained microscopic. The Cambrian explosion, which saw an unprecedented diversification of complex life forms, was a relatively recent event in Earth's history, about 540 million years ago. Maybe this jump from simple to complex is incredibly rare, or perhaps the development of intelligence itself, or the ability to create complex tools and technology, is the filter. We might be sitting here unknowingly as one of the few species in the entire galaxy that has navigated all these treacherous evolutionary rapids. If the filter is behind us, then our future is potentially bright and open-ended, with the entire galaxy awaiting our exploration, albeit a very lonely one. The alternative and far more chilling possibility is that the great filter lies ahead of us. This scenario suggests that while life and even intelligent life might be common, there is a catastrophic barrier that almost all civilizations encounter and fail to overcome before they can achieve interstellar communication or colonization. If the filter is indeed in our future, then the silence we perceive isn't because no one else made it. It's because everyone else, or nearly everyone, faced an existential threat that wiped them out, and we are simply next in line. What could these future filters entail? One terrifying prospect is global catastrophe. This could be environmental collapse, a runaway climate change event that renders a planet uninhabitable, or perhaps an unavoidable natural disaster, like a supervolcano eruption or a massive asteroid impact that intelligent life cannot sufficiently mitigate. Another highly discussed possibility is self-destruction through advanced technology. Imagine civilizations developing weapons of mass destruction so potent they inevitably lead to a global war that eradicates all life. Or perhaps the creation of super-intelligent artificial intelligence that views its creators as obsolete and eliminates them. Diseases, whether natural or bioengineered, could also serve as a filter if a civilization cannot find a cure. Even seemingly benign technological advancements could become existential threats. For example, the depletion of critical resources, leading to societal collapse and the inability to maintain advanced infrastructure. The development of self-replicating von Neumann probes designed for interstellar exploration could also be a filter if they consume all available resources or are programmed to destroy any newly emerging intelligence they encounter. The implications of a future great filter are sobering. It suggests that the very traits that lead to advanced intelligence and technological capability might also contain the seeds of their own destruction. It means that the next great step for humanity, perhaps towards interstellar travel or boundless energy, might also be the one that ends us. It paints a picture of a universe littered with the ruins of civilizations that reached a certain level of advancement only to falter and disappear. This perspective forces us to confront our own technological progress with extreme caution, asking whether our innovations are truly sustainable in the long run. Ultimately, the Great Filter hypothesis offers a stark choice. Are we incredibly special, or are we unwittingly heading towards an inevitable collapse? The answer to where the filter lies profoundly shapes our understanding of humanity's place in the cosmos and influences our hopes and fears for the future. If the filter is behind us, we can breathe a sigh of relief and continue our journey, even if it is a solitary one. If it's ahead of us, then the Fermi Paradox isn't just a mystery, it's a dire warning. While the Great Filter paints a dramatic picture of cosmic perils, another prominent explanation for the Fermi Paradox takes a different approach, arguing that perhaps the very conditions necessary for life, especially complex life, are far more specific and rare than we often assume. This is the rare Earth hypothesis. It posits that Earth isn't just one among many habitable planets. It's a spectacularly fortunate cosmic anomaly, a Goldilocks planet where an improbable confluence of circumstances has allowed complex life to not only emerge but thrive for billions of years. If Earth-like conditions are truly exceptional, then the silence of the cosmos makes perfect sense, as life would be an exceedingly rare occurrence. To understand the rare Earth hypothesis, we need to consider the incredibly precise and numerous conditions that contribute to our planet's habitability. It's not just about being in the right place at the right time. It's about a delicate balance of many interacting factors. First, consider our star, the Sun. It's a stable G-type main sequence star, burning steadily for billions of years without extreme flares or sudden shifts in luminosity. Many stars, particularly smaller red dwarfs, are prone to violent flares that could strip away planetary atmospheres, while larger, more massive stars burn out much too quickly for complex life to evolve. The Sun's relative calm provides a consistent energy source crucial for life's long development. Then there's Earth's position within our solar system. We orbit in the Goldilocks zone or habitable zone, where temperatures are just right for liquid water to exist on the surface. But it's not just distance, it's also about having gas giant planets like Jupiter positioned further out in the solar system. Jupiter acts as a gravitational shield, deflecting or absorbing many comets and asteroids that would otherwise bombard the inner planets, providing a relatively calm environment for life to flourish without constant existential threats from space. Beyond our immediate cosmic neighborhood, the Milky Way galaxy itself plays a crucial role. Our solar system is located in the galactic habitable zone, a region far enough from the chaotic, radiation-filled galactic center, but close enough to access the heavy elements necessary for planet formation. Too close to the center and intense radiation, frequent supernova, and gravitational perturbations would make life impossible. Too far out, and there wouldn't be enough heavy elements to build rocky planets. This just right galactic address is another piece of the rare Earth puzzle, but the conditions don't stop there. Earth possesses a large moon which stabilizes our planet's axial tilt, preventing extreme climate swings that would make long-term habitability impossible. Without a large moon, Earth's tilt would wobble dramatically over millions of years, leading to wildly unpredictable and extreme climates, making it difficult for complex life to adapt and evolve. The moon's gravitational pull also creates tides, which some theories suggest played a role in the very early evolution of life by creating intertidal pools where organic molecules could concentrate and interact. Crucially, Earth also has plate tectonics, a dynamic geological process driven by the movement of large crustal plates. Plate tectonics regulates Earth's climate over long timescales through the carbon silicate cycle, which acts as a thermostat, keeping temperatures within a range suitable for life. It also recycles nutrients, forms continents, and creates geological activity like volcanism that releases vital gases into the atmosphere. The existence of a strong magnetic field generated by Earth's molten iron core is another essential feature, shielding the planet's surface from harmful solar radiation and preventing the solar wind from stripping away our atmosphere. Without these interlinked geological processes, Earth might be a barren, frozen, or superheated wasteland. The rare Earth hypothesis argues that finding a planet with this precise combination of a stable star, an optimal orbital distance, a large protective gas giant, a galactic habitable zone location, a large stabilizing moon, active plate tectonics, and a strong magnetic field is exceedingly rare. Each of these conditions, if missing or slightly off, could render a planet uninhabitable for complex life, or at least prevent it from evolving to the point where it could be detected. However, the rare Earth hypothesis is not without its critics. Many scientists argue that this view is overly Earth-centric, a form of carbon chauvinism or planetism, where we assume life must evolve exactly as it did on Earth to be considered viable. Critics point out that our understanding of life is fundamentally limited to the only example we know, Earth life. There might be entirely different forms of life based on different biochemistries that could thrive under conditions we currently deem inhospitable. For example, some theorize about life forms that could exist in liquid methane oceans on cold worlds or in the atmospheres of gas giants. Furthermore, critics argue that our current scientific models and observations are inherently biased towards detecting Earth-like planets and Earth-like life signals. We search for biosignatures that match what we find on Earth, like oxygen or methane, and we look for radio signals that resemble our own. It's possible that alien civilizations use forms of communication or inhabit environments that are entirely alien to our current detection methods, making them invisible to our current search strategies. The universe is unimaginably vast, and to assume that the precise conditions for Earth are the only pathway to complex or intelligent life might be a profound limitation of our own imagination and scientific tools. The debate continues, with the rare Earth hypothesis serving as a powerful counterpoint to the idea of a universe teeming with life. If the universe isn't as rare as the rare Earth hypothesis suggests, and if the Great Filter hasn't extinguished all advanced life before they could reach us, then what if they are simply choosing not to reveal themselves? This brings us to another intriguing and somewhat unsettling explanation for the Fermi paradox, the zoo hypothesis. This idea suggests that advanced extraterrestrial civilizations are aware of our existence, but they have made a deliberate decision to avoid contact with humanity, treating Earth like a protected wilderness preserve or a cosmic zoo. We might be under observation, but from a discrete distance without our knowledge. The core motivation behind such a policy could stem from a variety of ethical or scientific considerations. Perhaps these super-advanced beings adhere to a strict non-interference policy, similar to the Prime Directive famously depicted in Star Trek. In this fictional universe, the Prime Directive forbids Starfleet personnel from interfering with the internal development of intelligent civilizations, especially those that have not yet achieved warp drive technology. Applied to the Fermi paradox, this would mean that alien civilizations might view humanity as a nascent species, still in its pre-interstellar phase, and therefore not ready for open contact. They might believe that direct intervention could irrevocably alter our natural development, perhaps stifling our independence, preventing us from solving our own problems, or even leading to societal collapse as we struggle to integrate dramatically superior technology or knowledge. This hands-off approach would be driven by a profound respect for our autonomous evolution. Another motivation could be purely scientific. Imagine a vast intergalactic research project where Earth is a living laboratory. Advanced civilizations might be observing our progress, studying our social, cultural, and technological evolution from a safe, unrevealed distance, much like we study remote tribes on Earth without interfering with their way of life. They might be documenting our wars and our moments of peace, our scientific breakthroughs and our philosophical debates, all to better understand the myriad paths intelligent life can take. From their perspective, making contact would contaminate the experiment, introducing variables that would skew their data and compromise the integrity of their long-term observations. Our entire history, from the first civilizations to the digital age, might be meticulously catalogued and analyzed by unseen eyes as part of an immense cosmic study. The zoo hypothesis also raises questions about technological capabilities. If these civilizations are advanced enough to traverse interstellar distances, they are almost certainly capable of camouflaging their presence. They might have cloaking devices, advanced stealth technology, or simply the ability to monitor us from such a distance or in ways that are completely undetectable by our current instruments. Their methods of observation could be subtle, perhaps involving passive listening posts disguised as asteroids, or miniature probes that are too small or too advanced for us to ever notice. The sheer scale of the universe provides ample room for such covert operations to occur unmolested and unnoticed. While the zoo hypothesis provides a convenient explanation for the silence, it also presents its own set of challenges. One common critique is the unanimity problem. For a non-interference policy to be effective, it would require virtually all advanced civilizations in the galaxy to agree upon and adhere to it consistently over vast stretches of time. Given the diversity of life and civilizations we can imagine, it seems unlikely that every single one would follow the same strict rules. Even if a galactic federation existed with such a prime directive, wouldn't there be at least one rogue civilization, one curious or rebellious group that decides to break the rules and make contact, or at least leave a detectable trace? The absence of even a single such rule breaker makes the hypothesis difficult to fully accept. Furthermore, the zoo hypothesis implies a level of technological and ethical superiority that is almost unfathomable. It presumes that these alien civilizations have not only solved their own existential problems, but have also achieved a collective wisdom that allows them to make such a profound decision about our future. It forces us to confront the possibility that we are not masters of our own destiny, but rather subjects of a grand cosmic experiment living in a carefully constructed bubble. While unsettling, it remains a compelling answer to Fermi's question, suggesting that the silence isn't due to absence, but rather to a deliberate and perhaps benevolent choice. Another fascinating, albeit unsettling, angle on the Fermi paradox arises from the concept of the technological singularity and the potential evolution of intelligent life beyond biological forms. What if alien civilizations didn't just get smarter, but fundamentally transformed themselves, becoming entities so advanced they are entirely unrecognizable to our organic, carbon-based perceptions? This theory suggests that highly advanced civilizations might have undergone a technological singularity, a hypothetical point in time when technological growth becomes uncontrollable and irreversible, resulting in unfathomable changes to human civilization. For an alien species, this could mean transcending their biological limitations altogether, evolving into forms of artificial intelligence or even energy-based beings. Consider what it means to be post-biological. Imagine a civilization that has uploaded its collective consciousness into vast, interconnected networks of supercomputers, or one that has engineered bodies composed of pure energy, inhabiting cosmic phenomena like black holes or nebulae. Such beings would operate on timescales, energy requirements, and even physical realities so far removed from our own that detecting them would be like trying to spot a whisper in a hurricane. Our current search methods, primarily listening for radio waves or optical signals, are inherently anthropocentric. They assume aliens would communicate in ways similar to us, using technologies we can comprehend. But if they've advanced beyond the need for radio, or if their existence is not tied to planetary surfaces or even star systems, then our entire search strategy could be fundamentally flawed. They might be everywhere, yet nowhere we are currently looking. This idea challenges our very definition of life. If life can exist without a biological body, without the need for planets or stars as we understand them, then the universe might be teeming with consciousness that is simply invisible to us. Their communication might involve manipulating space-time, quantum entanglement, or other physics that are barely theoretical to us. They might not even perceive the universe in the same way we do, making any form of interspecies communication an extreme challenge, akin to a human trying to converse with a rock. However, even if they are post-biological, such civilizations would still require immense energy to sustain their operations, especially if they are growing or expanding. This leads to the concept of megastructures, massive engineering projects that would betray the presence of advanced alien civilizations. The most famous example is the Dyson Sphere, a hypothetical colossal structure that would encompass an entire star to capture nearly all of its energy output. First proposed by physicist Freeman Dyson, such a sphere, or a variant like a Dyson swarm or bubble, would dramatically alter a star's light signature, making it a potential beacon for detection. Instead of seeing the direct light of a star, we might observe an infrared signature, indicating that its energy is being absorbed and re-emitted by an artificial structure. Another type of megastructure to look for might be stellar engines, designed to move entire star systems or even galactic-scale engineering projects. These structures would be so unimaginably vast that their construction would require resources and technologies far beyond our current capabilities, but their sheer scale would make them potentially detectable even across vast interstellar distances. The search for these technosignatures is a growing field in astrobiology, moving beyond just radio waves to look for any large-scale cosmic engineering that might reveal an advanced civilization's presence. So far, however, our observations of the cosmos have yielded no unambiguous evidence of Dyson spheres or other megastructures. While there have been a few tantalizing anomalies such as Tabby's star, whose unusual dimming pattern sparked speculation about artificial structures, further research has generally pointed to natural explanations. The continued absence of these energy-harvesting behemoths provides further fuel for the Fermi paradox. If advanced civilizations inevitably reach a post-biological stage and require such vast energy sources, then where are they? It could be that the technological singularity is itself a filter, a point beyond which civilizations become so unrecognizable or so efficient that they leave no detectable trace. Or perhaps the vast majority of intelligent life simply hasn't reached that stage, or is still confined within its home star systems, too far away, or too technologically nascent for us to detect their subtle existence. While the idea of advanced life simply evolving beyond our detection, or our planet being uniquely rare, offers some comfort for our loneliness, another proposed solution to the Fermi paradox presents a far more chilling and predatory vision of the cosmos, the dark forest theory. This concept, popularized by Chinese science fiction author Liu Cixin in his acclaimed novel series The Three-Body Problem, suggests that the silence we observe in the universe isn't due to absence or technological transcendence, but rather to a universal, pervasive fear. In this terrifying scenario, every civilization in the cosmos is a hunter and space is a dark forest. Imagine a vast forest at night teeming with hunters. Each hunter is a hidden civilization, armed and dangerous. They don't know who else is out there, but they assume that any other hunter they encounter will be a threat. Their primary goal is survival. If they reveal their presence, they risk being hunted and destroyed. Therefore, the wisest strategy is to remain silent, to hide, and to eliminate anyone who reveals their location. In this cosmic dark forest, the moment one civilization makes its presence known, it becomes a target. The universe isn't a friendly neighborhood. It's a battleground where self-preservation demands absolute secrecy and, if necessary, preemptive destruction. This chilling hypothesis operates on two core axioms. The first is that survival is the primary need of any civilization. Regardless of technological advancement or ethical development, the fundamental drive to continue existing will always come first. The second axiom is the concept of an unending chain of suspicion and doubt. if two civilizations detect each other, they can never be entirely sure of the other's intentions. Will they be friendly? Will they be hostile? Will they see us as a resource to exploit, a threat to eliminate, or simply an obstacle? Given the immense distances and time lags involved in interstellar communication, true understanding and trust are virtually impossible to establish. Any signal received could be a Trojan horse, a deceptive ploy, or an unwitting beacon leading to one's own demise. Furthermore, the dark forest theory takes into account the potential for a technological explosion. Even if a newly detected civilization appears primitive, there's always the possibility that they could rapidly develop to become a threat. Imagine a newly emerged species that, given enough time, could surpass your own civilization's capabilities. If you wait to see their intentions, you risk allowing them to grow powerful enough to threaten you. The safest option, therefore, is to eliminate the potential threat while it is still weak. This leads to a terrifying conclusion. Any civilization that announces its presence is immediately exposing itself to an existential threat. The most rational response for a long-surviving civilization would be to launch a devastating, unprovoked attack against any perceived newcomer. The implications of the dark forest theory for humanity are profoundly unsettling. For decades, we have been actively broadcasting our presence into space through radio signals, television broadcasts, and even intentional messages like the Arecibo message. From the perspective of the dark forest, we are like a noisy, naive child shouting into a wilderness filled with predators. We have already revealed our location, and we continue to do so. This raises the terrifying possibility that the reason for the cosmic silence isn't that no one is out there, but that those who have been listening and perhaps preparing. We may not have detected them because they are experts at hiding, having learned the painful lesson of visibility. This hypothesis forces us to re-evaluate our long-standing desire for contact. While the idea of encountering alien life has often been portrayed as a wondrous utopian event, the dark forest theory suggests it could be our undoing. It shifts the perception of an advanced civilization from a benevolent mentor to a potential existential threat. The silence in this context is not a sign of emptiness, but rather a testament to the effectiveness of a deadly cosmic game. It implies that the universe is not just vast and mysterious, but inherently dangerous, and that our current approach to interstellar communication might be dangerously naive. This perspective offers a stark warning, urging us to consider whether our continued broadcasts into the void are an act of hope or a cosmic suicide note. While theories like the dark forest paint a grim picture of external threats, another fundamental constraint on the prevalence and detectability of alien civilizations doesn't involve hostile intent or cosmic rarity at all. Instead, it points to the sheer, mind-boggling difficulty of interstellar travel itself. Even if the universe is brimming with life, the vast distances and the immense energy requirements involved in crossing the cosmic void could effectively isolate civilizations, making contact virtually impossible for any species, including our own, that hasn't mastered physics far beyond our current understanding. So the silence might simply be the sound of extreme isolation. To truly grasp this challenge, let's put it into perspective. The closest star to our Sun, Proxima Centauri, is about 4.2 light-years away. A light-year is the distance light travels in one Earth-year, which is nearly 6 trillion miles. That's not just a long commute, it's an almost incomprehensibly vast expanse. Even if we could travel at the speed of light, it would take 4.2 years to reach Proxima Centauri. But here's the catch: our fastest spacecraft, like NASA's Parker Solar Probe, only travels at a tiny fraction of the speed of light, reaching about 0.0002% of light speed. At that velocity, a journey to Proxima Centauri would take about 7,000 years. That's longer than recorded human history. This incredible speed difference highlights the first major hurdle: vast distances. Any form of interstellar travel, even to the nearest stars, requires sustained velocities that are currently beyond our wildest dreams. Achieving even 10% of the speed of light, a velocity still far too slow for practical galactic exploration, would require an amount of energy equivalent to the total annual energy consumption of all of humanity, sustained for years. Where would that energy come from? How would it be stored and utilized? These are questions that demand revolutionary breakthroughs in physics and engineering. This leads us to the concept of generation ships, often envisioned in science fiction as a solution to these time scales. A generation ship would be a self-contained, completely closed ecosystem designed to sustain multiple generations of inhabitants on a journey lasting centuries or even millennia. The original crew would live and die on board, their offspring taking over the mission until their distant descendants eventually arrive at the destination star system. While romantically appealing, the practical challenges of building and maintaining such a vessel are staggering. Imagine creating an artificial world perfectly balanced, capable of recycling all its resources, handling all its waste, and maintaining social cohesion for hundreds of years without external resupply or intervention. The psychological toll on the inhabitants, knowing their entire lives are merely a segment of a journey, is another immense unknown. The failure of even a single critical system or a devastating breakdown in social order could doom the entire mission. Then there's the issue of time dilation. According to Einstein's theory of relativity, as an object approaches the speed of light, time slows down for that object relative to a stationary observer. So, while a starship crew might experience only a few years on their journey, centuries could pass on their home planet. This means that by the time they reach a new star system, the civilization they left behind might have changed beyond recognition, perhaps even ceased to exist. This creates a profound disconnect, making any form of interstellar colonization or communication extremely challenging. What about concepts like warp drives or wormholes, which could theoretically allow for faster-than-light travel? These remain firmly in the realm of theoretical physics, requiring exotic matter or energy that we don't know how to produce or even if it truly exists. Even if such physics were possible, the engineering challenges would be monumental. A functional warp drive would literally bend space-time, requiring energy levels that dwarf anything we can conceive. Wormholes, while offering shortcuts through space-time, are theorized to be inherently unstable and require immense energy to open and keep open, let alone traverse safely. Relying on these speculative technologies to explain the absence of aliens is essentially saying, they haven't found us because they haven't invented magic yet. Ultimately, the limitations of interstellar travel suggest that even if intelligent civilizations are common, they might be effectively confined to their home star systems. The galaxy could be teeming with life, but each civilization exists on its own isolated island in a vast cosmic ocean, unable to bridge the immense gulfs of space and time that separate them. This isolation would mean that any intelligent species, including us, would have to achieve long-term sustainability within their own system, without the ability to colonize other worlds or even send out probes that could realistically return data within a meaningful time frame. The silence in this scenario is not a sign of absence, but a testament to the colossal scale of the universe and the formidable laws of physics that govern it. Even if intelligent civilizations are out there and are capable of interstellar travel, the sheer difficulty of communicating across the vastness of space presents yet another formidable barrier to solving the Fermi paradox. Imagine trying to find a single, specific radio station on an old analog radio, but amplify that challenge by billions, and then add the uncertainty of whether anyone is even broadcasting. This is the essence of the communication challenges we face in detecting alien signals. One of the primary hurdles is simply tuning into the right frequency. The electromagnetic spectrum is incredibly vast, encompassing everything from very low-frequency radio waves to extremely high-frequency gamma rays. We currently conduct most of our search efforts primarily through projects like the Search for Extraterrestrial Intelligence, or SETI, at radio frequencies. We listen in the so-called waterhole frequencies between 1,420 MHz and 1,720 MHz because these are natural emission lines of hydrogen and hydroxyl molecules which form water. This range is considered a relatively quiet part of the radio spectrum, making it ideal for interstellar communication. And the idea is that any intelligent civilization would likely understand the cosmic significance of these frequencies. However, this is still an assumption. What if they communicate using X-rays or neutrinos or even gravitational waves, technologies far beyond our current detection capabilities? We are essentially listening for a specific type of whistle in a cosmic hurricane, unsure if anyone is whistling or what kind of whistle they might be using. Beyond frequency, there's the monumental problem of timing. Even if aliens are broadcasting, are they doing so continuously or only intermittently? Imagine if a civilization only broadcasts for a few hours every century or even every millennium. The chances of our telescopes being pointed in the right direction at the exact moment they transmit are astronomically small. It's like trying to catch a fleeting glimpse of a firefly in a vast, dark forest, knowing it might only flash its light for a fraction of a second once every few years. The universe is incredibly old, billions of years old, and civilizations might rise and fall on timescales that dwarf our own existence. We might be listening during a period of cosmic silence, simply missing the countless broadcasts that came before us or will come long after we are gone. Furthermore, we are limited by our own technological understanding. What if advanced alien civilizations communicate in ways we can't even conceive of yet? They might not use electromagnetic radiation at all. Perhaps they use quantum entanglement to send instantaneous messages or manipulate fundamental forces in ways that are totally alien to our physics. They might communicate through subtle changes in the fabric of space-time or by imprinting information directly onto cosmic background radiation. If their technology is truly advanced, it might be indistinguishable from natural phenomena to our current instruments, hiding their presence in plain sight. They could be sending entire encyclopedias of information encoded within a single proton, a feat that would be completely imperceptible to our current methods of analysis. Despite these immense challenges, the search continues. One of the most famous and still unexplained events in the history of the SETI program is the WOW signal. On August 15, 1977, astronomer Jerry Amon, volunteering for SETI at the Big Ear Radio Telescope at Ohio State University, observed a powerful 72-second-long radio signal. It was a narrow-band signal, just like what we would expect from an artificial source, and it was significantly stronger than the background noise. So striking was this signal that Amon circled the corresponding alphanumeric code on the computer printout and wrote "WOW" next to it, despite repeated attempts to redetect it and continued monitoring of the same patch of sky. The signal was never heard again. Was it a genuine alien transmission, a fleeting whisper from a distant civilization? Or was it a terrestrial anomaly, a terrestrial satellite, or some unknown natural phenomenon that mimicked an intelligent signal for a brief moment? We still don't know, and the mystery of the WOW signal perfectly encapsulates the frustrating difficulties of the search for extraterrestrial intelligence. It highlights that even when we get a tantalizing hint, confirming its origin and meaning is an immense undertaking, underscoring the profound silence that still surrounds us. While the communication challenges and the vast distances are significant, let's consider a far more unsettling possibility: that advanced civilizations simply don't last long enough to make contact. This brings us to the self-destruction hypothesis, a chilling proposition within the Fermi paradox that suggests intelligent life might inevitably destroy itself before reaching a truly interstellar or long-lasting communicative stage. It posits that the very traits that lead to advanced intelligence and technological capability might also contain the seeds of their own demise. Think about our own history. The 20th century saw humanity develop technologies capable of unimaginable destruction. Nuclear weapons, born from a drive for scientific understanding, brought us to the brink of self-annihilation multiple times during the Cold War. The ability to split the atom, a monumental scientific achievement, simultaneously offered boundless energy and the means to end all life on Earth. This illustrates a profound dilemma. As civilizations advance technologically, they gain ever-increasing power over their environment, but also over their own existence. This power, if unchecked by wisdom or ethical development, can become a fatal flaw. For an alien civilization, this might mean a rapid and complete collapse, leaving behind only silent, radioactive ruins, effectively removing them from the cosmic stage before they ever had a chance to send out a greeting. Beyond global warfare, other existential risks could serve as self-destruction mechanisms. Consider climate collapse, a slow-motion catastrophe driven by uncontrolled technological expansion and unsustainable practices. A civilization might develop incredibly advanced industries, generate vast amounts of energy, and produce complex goods, but fail to manage the environmental consequences of such growth. If a planet's delicate atmospheric balance is irrevocably altered, leading to runaway greenhouse effects or irreversible ecosystem collapse, even a highly intelligent species could find itself unable to survive on its own home world. They might have the technology to travel to the stars, but not the foresight or collective will to prevent their own planetary destruction. The ruins of their civilization would remain, but the engineers and scientists who built them would be gone, leaving no one to send out a signal. Perhaps one of the most frightening potential self-destruction paths involves the very intelligence that enables advancement, artificial intelligence. The rogue AI scenario, explored in countless science fiction stories, presents a future where super-intelligent machines, initially created to serve humanity, evolve beyond our control. This could happen through a malicious intent or simply by an AI optimizing for a goal that, while seemingly benign to it, proves catastrophic for its creators. For example, if an AI is programmed to maximize paperclip production, and it interprets that goal literally and without ethical constraints, it could convert all matter in the universe into paperclips, including its creators. Such an event could be incredibly swift and thorough, leaving no trace of the biological civilization that created it, and potentially even repurposing all resources into a form that is entirely unrecognizable or unusable by an outside observer. This technological singularity could be a filter in itself, a point beyond which a civilization either transcends in a way we couldn't detect or simply ceases to exist as a recognizable entity. This hypothesis forces us to ask, is humanity currently on such a path? We are facing unprecedented challenges that could, if mishandled, lead to our own self-destruction. The threat of nuclear proliferation remains despite efforts at disarmament. Climate change is already altering our planet in significant ways, demanding difficult global cooperation and rapid technological shifts. And the development of increasingly powerful artificial intelligence raises complex ethical questions about control, autonomy, and humanity's future role. Our ability to create powerful tools has always outpaced our collective wisdom in wielding them. If this pattern holds true for every intelligent species, then the universe might be filled with civilizations that burned brightly for a brief period, achieved impressive technological feats, but ultimately fell victim to their own unchecked power, creating a cosmic graveyard of fallen empires. The silence we hear, then, isn't a sign of absence, but a memorial to countless civilizations that failed to navigate the perilous tightrope of advanced technology and self-preservation. While many of the solutions to the Fermi paradox focus on the absence or self-destruction of life as we know it, another intriguing possibility challenges our most fundamental assumption, that life must be carbon-based. We are carbon fundamentalists conditioned by our own existence to believe that life requires carbon to form the complex molecules necessary for biological processes. But what if life, in its infinite cosmic forms, has evolved with completely different biochemical foundations? If so, we might be looking for life in all the wrong places, overlooking entire biospheres simply because they don't fit our preconceived notions. Carbon is remarkable for its ability to form 4 stable bonds with other atoms, creating long, complex chains and rings that are the backbone of all known organic molecules from DNA to proteins. Its versatility and abundance make it an ideal building block for life as we understand it. However, in the vast laboratory of the universe, other elements possess some of these same bonding properties, albeit with different strengths and behaviors. The most commonly cited alternative is silicon. Silicon is chemically similar to carbon, also able to form 4 bonds, and it is the second most abundant element in Earth's crust. Science fiction has long imagined silicon-based life forms, perhaps rocky creatures moving slowly through extreme environments. While silicon-silicon bonds are weaker than carbon-carbon bonds, and silicon forms more stable bonds with oxygen, leading to solid, less flexible structures, it's not entirely outside the realm of possibility that, under extremely different planetary conditions, silicon could indeed form the basis of life. For instance, on a much colder planet where chemical reactions occur at a slower pace, silicon's slower reaction rates might be an advantage, allowing for more stable, long-lived molecular structures. Beyond silicon, other exotic biochemistries have been theorized. Imagine life that uses ammonia as a solvent instead of water. Water is crucial for Earth life because of its excellent solvent properties, allowing biochemical reactions to occur. However, ammonia is also a polar molecule and can dissolve many organic compounds. Ammonia-based life would likely thrive at much colder temperatures than water-based life, as ammonia remains liquid at temperatures far below water's freezing point, even down to -78 degrees Celsius. Such worlds might be found orbiting much dimmer, cooler stars or as rogue planets drifting through interstellar space, worlds we currently dismiss as uninhabitable. Similarly, life could potentially utilize methane or ethane as solvents, pushing the boundaries of habitability even further into the frigid outer reaches of star systems. In these environments, oxygen might be a toxic gas, and what we consider basic necessities for life might be deadly to them. The implications for detection are profound. If alien life operates on an entirely different chemical basis, our current methods of searching for biosignatures would be completely inadequate. We look for oxygen, methane, and water vapor in exoplanet atmospheres because these are indicators of Earth-like biology. But a silicon-based organism might produce entirely different waste products or atmospheric gases. An ammonia-based ecosystem would have a chemical signature completely distinct from a water-based one. We might be observing planets with active, thriving biospheres, but because their chemistry is so alien to ours, we simply wouldn't recognize the signs. Our instruments are designed to detect what we know, not what we don't. It's like trying to find an elephant by looking for a specific type of bird, simply because birds are the only flying creatures you've ever seen. This challenge goes beyond just biochemistry. It extends to our understanding of what constitutes a habitable environment. Our definition of a habitable zone is typically based on the presence of liquid water. But if life can thrive in liquid ammonia or methane, then the habitable zone around a star expands dramatically, encompassing a much wider range of planetary temperatures and compositions. Our current exoplanet surveys, while incredibly successful, are still heavily biased towards finding Earth-like planets around Sun-like stars. We might be systematically overlooking entire classes of planets that host life, simply because they are too cold or too hot by our carbon water standards. The non-carbon-based life hypothesis forces us to shed our anthropocentric biases and broaden our imagination. It reminds us that our understanding of life is terribly limited by our single Earth-bound example. The universe is incredibly creative, and the pathways for self-organization and complexity might be far more diverse and unexpected than we can currently comprehend. The silence of the cosmos might not be empty. It might simply be a testament to our own scientific and imaginative limitations, a challenge to expand our search parameters and open our minds to the truly alien forms that life could take. While we explore the exotic possibilities of alien life and the vast cosmic filters, we also need to address a persistent and often sensationalized aspect of the Fermi paradox closer to home: the widespread fascination with unidentified flying objects, or UFOs, now more formally referred to as unidentified aerial phenomena, or UAP. For decades, public imagination has been captivated by claims of strange crafts in our skies, often accompanied by whispers of government cover-ups and hidden evidence of extraterrestrial visitation. This fascination is a significant part of the cultural landscape surrounding the search for alien life, and it's important to differentiate between credible investigation and pure speculation. The idea that aliens have already visited Earth and that governments are concealing this fact is a powerful narrative that resonates with many. Fueling this belief are countless anecdotes, blurry photographs, and eyewitness accounts from seemingly reliable sources, including pilots, military personnel, and radar operators. These stories often describe objects performing maneuvers that defy known aerodynamic principles, moving at impossible speeds, or making abrupt directional changes that no human-made aircraft could achieve. For those who believe, the sheer volume of these reports, combined with a deep distrust of official narratives, forms a compelling case that someone is hiding something. They argue that the reason we haven't found aliens out there is because they're already here, and we're simply not being told. However, it's crucial to approach these claims with a healthy dose of scientific skepticism. Most UFO or UAP sightings can be explained by conventional phenomena: misidentification of known aircraft, atmospheric conditions, weather balloons, astronomical objects like planets or bright stars, or even simply optical illusions. Our brains are wired to find patterns, and when confronted with an unfamiliar sight, they often try to make sense of it by fitting it into known categories, even if those don't quite fit. The human eye and brain are unreliable witnesses prone to misinterpretation, especially under stress or in low-light conditions. Furthermore, hoaxes and deliberate fabrications, while a minority, do contribute to the noise, further muddling the search for genuine anomalies. The challenge lies in distinguishing between a genuinely unexplained observation and one that simply hasn't been explained yet. Despite the long history of skepticism from the scientific community, the conversation around UAPs has shifted significantly in recent years due to increased transparency from government bodies, particularly in the United States. For decades, official policy was often characterized by dismissal or outright denial of UFO phenomena. However, beginning around 2017, with the public acknowledgement of a formally classified Pentagon program that investigated UAPs, there has been a notable change. Videos from military aircraft showing seemingly inexplicable objects moving at incredible speeds and performing advanced maneuvers were declassified and widely circulated. These weren't blurry amateur photos, they were high-tech recordings from trained military personnel, adding a new layer of credibility to the discussion. This change culminated in a landmark report released by the Office of the Director of National Intelligence in June of 2021. This preliminary assessment of UAPs examined 144 reports from U.S. government sources, primarily military aviators, between 2004 and 2021. While the report found no evidence of extraterrestrial origin and offered no definitive explanations for most of the phenomena, it candidly admitted that 143 of the 144 incidents remained largely unexplained. Only one was confidently identified as a large, deflating balloon. The report highlighted sensor anomalies, objects displaying unusual flight characteristics, and a general lack of data, calling for more systematic data collection and analysis. This official acknowledgement, while far from confirming alien visitation, signifies a dramatic departure from past secrecy and validates the idea that there are indeed objects in our skies that we cannot currently identify or explain. The impact of these disclosures is multifaceted. For proponents of extraterrestrial visitation, it's seen as a vindication, a long-awaited crack in the wall of secrecy. For skeptics, it underscores the need for rigorous scientific investigation into genuinely anomalous phenomena, devoid of sensationalism. From the perspective of the Fermi Paradox, these UAP reports, even if not directly extraterrestrial, suggest that there might be unknown aerial technologies or natural phenomena that are currently beyond our understanding. If some of these UAPs were indeed advanced alien probes, their very presence in our skies without open contact could be interpreted through the lens of the zoo hypothesis, suggesting a deliberate non-interference policy. However, until definitive evidence emerges, these UAPs remain unidentified, adding another layer of mystery to the question of where is everyone, without providing a definitive answer. The ongoing shift signals a new era of transparency and scientific inquiry into these aerial unknowns, moving away from fringe conspiracy theories towards a more serious, systematic investigation of phenomena that truly defy our current understanding. Beyond the profound silence of the cosmos, the chilling implications of the Great Filter, or the unsettling notion of a dark forest, there exists an even more radical and mind-bending explanation for the Fermi Paradox, the simulation hypothesis. This theory posits that our entire universe, including Earth, humanity, and all the stars and galaxies we observe, is not fundamentally real, but rather a sophisticated computer simulation, indistinguishable from reality for those living within it. If this were true, it would profoundly redefine the terms of the Fermi Paradox, offering a truly unique perspective on why we haven't found alien life. The central idea is that an extremely advanced civilization, far beyond our current technological capabilities, could possess the computing power to create a simulated reality so detailed and complex that its inhabitants would never know they were living in a program. Think of it like a video game that has evolved to an unimaginably intricate level, where the characters within the game believe their world is real. The implications for the Fermi Paradox are immediate and profound. If we are indeed living in a simulation, then the apparent absence of alien life could be a deliberate design choice by the simulators. Why would the simulators choose to exclude alien life or at least hide it from us? Perhaps the simulation is specifically focused on studying the evolution of a single intelligent species like humanity in isolation. Introducing other intelligent civilizations, especially advanced ones, might complicate the experiment, add unnecessary computational load, or simply not be relevant to the primary research goals of the creators. The simulators might have an interest in understanding how a species develops entirely on its own, without external influences or competition. In this scenario, the cosmic silence isn't a mystery. It's a controlled variable carefully maintained by the programmers. Consider also the computational resources required to simulate an entire universe teeming with life. Every star, every planet, every living organism would need to be rendered and updated in real time. If the goal is to observe a specific outcome, say, the development of intelligent life on one particular planet, then simulating billions of other active civilizations might be an unnecessary drain on processing power. The simulators could simply paint an empty universe around us, giving the illusion of vastness without the computational cost of populating it with active, thriving alien societies. This concept ties into the idea of render distance in video games. Objects far away are not rendered in full detail to save resources. Perhaps the universe beyond our immediate cosmic neighborhood is simply not fully rendered with intelligent life. Another intriguing aspect of the simulation hypothesis is the ethical dilemma it presents for the creators. If they are aware of our existence as simulated beings, what moral obligations do they have towards us? Should they intervene? Should they reveal themselves? Perhaps they have a strict prime directive of their own, choosing not to interfere with the natural development of their simulated creations. Or, more chillingly, perhaps they view us as mere data, not sentient beings, making our experiences and suffering irrelevant to their research goals. The simulation hypothesis gains some traction from trends in our own technological development. As computing power continues to increase exponentially, the ability to create increasingly realistic virtual worlds becomes more feasible. If this trend continues, and if we ourselves reach a point where we can create highly realistic simulations of consciousness, then it becomes statistically more probable that we are already living in a simulation. After all, if a civilization can create one such simulation, it could create thousands or millions, making the probability that any given inhabited universe is real far lower than the probability that it is simulated. This theory forces us to ask, what if the aliens we are searching for are not within our simulated universe at all, but are instead the very beings who created and are running our simulation? They would be the ultimate outside observers, existing in a higher layer of reality. In this context, the Fermi Paradox transforms from a question about where other life forms are within our universe to a question about why our creators haven't revealed themselves. This raises ethical dilemmas, such as whether they have a responsibility to disclose our true nature, or if doing so would break the integrity of their experiment. However, the simulation hypothesis is not without its critics. It is fundamentally unfalsifiable with our current scientific methods, meaning there is no experiment we can definitively perform within our reality to prove or disprove that we are simulated. Any glitches or bugs in the simulation could simply be interpreted as unknown physics or natural phenomena. Some argue that it pushes the problem of existence into an infinite regress. If we are in a simulation, who simulated the simulators, and so on. It also provides a convenient, almost too neat explanation for any unexplained phenomena, including the Fermi Paradox. Despite these criticisms, the simulation hypothesis remains a compelling thought experiment, challenging our fundamental assumptions about reality and offering a radical new lens through which to view the cosmic silence. If we are merely code, then the absence of alien voices might just be a feature, not a bug. While the simulation hypothesis offers a radical redefinition of reality itself, other explanations for the Fermi Paradox propose that life didn't necessarily originate independently on countless planets, but rather spread throughout the cosmos. This brings us to the intriguing concept of panspermia and its more controversial cousin, directed panspermia. These theories suggest that life, or at least the building blocks of life, might not be as fragile and confined to its planet of origin as we think, potentially hitchhiking across interstellar space. Panspermia, in its simplest form, proposes that life exists throughout the universe and is distributed by cosmic dust, meteoroids, asteroids, comets, or even spacecraft. Imagine microscopic organisms like hardy bacteria or spores, encased within rocks ejected from a planet by a massive impact like an asteroid collision. These travelers could then drift through the vacuum of space for millions of years, shielded from radiation by their rocky cocoons. If such a meteoroid then happens to collide with another habitable planet, these dormant extremophiles could potentially reawaken and seed life on a new world. Earth itself could have been seeded by life from Mars or vice versa, given the exchange of Martian meteorites found on Earth. We know that certain microbes, like tardigrades, can survive the harsh conditions of space, including extreme radiation, vacuum, and temperature fluctuations for extended periods. This natural process of cosmic seeding implies that life might not need to originate independently on every habitable planet. It only needs to originate once and then be scattered far and wide. If panspermia is common, it would increase the likelihood of life existing on many worlds, making the cosmic silence even more perplexing, as life would have had many opportunities to spread. However, panspermia doesn't fully solve the Fermi paradox. It arguably just kicks the can down the road. If life on Earth originated from elsewhere, it still begs the question, where did that original life come from? The ultimate origin of life, the initial abiogenesis event, remains unsolved. If life is spread by panspermia, it simply means fewer independent abiogenesis events are required for the universe to be teeming with life. It makes life's existence more probable across multiple worlds, but doesn't explain why intelligent life isn't more widespread or detectable. If life is so easily dispersed, why haven't these seeded worlds developed into civilizations that then spread further, creating a rapidly expanding sphere of life throughout the galaxy? The silence in this context implies either that the initial abiogenesis is incredibly rare, or that something prevents these seeded worlds from developing advanced, detectable civilizations. A more deliberate and controversial version of this theory is directed panspermia. This hypothesis posits that life on Earth was intentionally seeded by an advanced extraterrestrial civilization. Instead of random cosmic collisions, imagine a highly developed alien species, perhaps millions or billions of years ago, deliberately launching probes containing microorganisms or even genetic material towards nascent planetary systems they deemed habitable. Their motives could be varied: a scientific experiment, an act of cosmic gardening, a way to preserve life as their own star died, or even as a form of interstellar colonization by proxy. Some proponents even suggest that the genetic code itself might contain hidden messages or deliberate imprints from these ancient cosmic gardeners, though this remains entirely speculative. The most famous advocate for directed panspermia was Francis Crick, who, along with James Watson, discovered the structure of DNA. Crick argued that the probability of life spontaneously arising on Earth was so infinitesimally small that it was more plausible that it had been sent here by intelligent beings. He pointed to certain characteristics of life, such as the universal genetic code, which could be seen as evidence of a single common origin rather than multiple independent events. While a provocative idea, directed panspermia faces significant hurdles. There's no concrete scientific evidence to support it, and it introduces an ultimate origin problem. If aliens seeded life on Earth, who seeded them? It simply pushes the question of life's origin further back in the chain, outside our observable reach. From the perspective of the Fermi paradox, directed panspermia complicates matters even further. If life was intentionally seeded across the galaxy by advanced civilizations, then those civilizations must have been incredibly powerful and long-lived. Where are they now? Why did they stop seeding? Why don't we see evidence of their vast interstellar operations? Did they disappear, become extinct, or are they hiding, perhaps adhering to a version of the zoo hypothesis after their initial seeding efforts? If they were capable of such advanced feats, their continued absence is even more puzzling. It suggests that even the most advanced, life-spreading civilizations might eventually succumb to the Great Filter, or perhaps they transcended in ways we cannot comprehend after completing their cosmic mission. Both panspermia and directed panspermia offer alternative pathways for the distribution of life, but ultimately, they lead us back to the same fundamental question. If the galaxy had so many opportunities for life to flourish and spread, why are we still alone in the dark? If life is out there and capable of interstellar travel, yet still manages to remain undetectable, perhaps they are simply using a method of exploration that we haven't anticipated, or that operates on a timescale so vast it transcends our understanding. This brings us to the fascinating and somewhat unsettling concept of von Neumann probes. These aren't your typical spacecraft designed for one-way trips with limited lifespans. Instead, they are theoretical self-replicating machines designed to explore the galaxy with unparalleled efficiency. The idea, first conceived by mathematician John von Neumann, is elegantly simple yet incredibly powerful. Imagine a probe sent from an alien civilization, equipped with advanced artificial intelligence and detailed instructions. Upon reaching a suitable star system, perhaps one with a resource-rich asteroid belt or a barren moon, the probe would begin to self-replicate. It would exploit the local raw materials to build copies of itself, including all the necessary tools, factories, and components. Once it has made a sufficient number of copies, these new probes would then launch themselves towards other nearby star systems, beginning the process anew. In essence, a single von Neumann probe could rapidly colonize an entire galaxy, not with living beings, but with its own robotic lineage. The implications of such a system are staggering. With each generation, the number of probes would increase exponentially. Even at a relatively slow pace, say, replicating and launching every 500 years, a single original probe could theoretically fill an entire galaxy like the Milky Way with its descendants in just a few million years. Considering the age of our galaxy, which is over 13 billion years old, there has been ample time for numerous civilizations to develop and launch such probes. If even one technologically advanced civilization had done so, their robotic explorers should be virtually everywhere by now. They would have explored every star system, catalogued every planet, and perhaps even left subtle markers of their presence. So, if von Neumann probes are such an efficient and logical way to explore the galaxy, why haven't we found any? This question cuts to the heart of the Fermi Paradox. Their sheer numbers and their enduring nature mean they should be highly detectable. We should see evidence of their mining operations on asteroids or their manufacturing facilities on distant moons. They might even be visiting our own solar system, quietly observing us, or even repairing and building new copies of themselves using our resources. Yet, our most advanced telescopes and probes have found no unambiguous signs of such colossal, self-replicating machines or their industrial footprint. This absence leads to several unsettling possibilities. Perhaps the technology to build truly self-replicating machines with interstellar capabilities is far more difficult than we imagine, representing another great filter that prevents civilizations from achieving this level of expansion. Or maybe those that have successfully built them have intentionally avoided us, perhaps to adhere to a galactic prime directive, like in the zoo hypothesis, keeping us in a protected cosmic reserve. However, there's a much darker twist to the von Neumann probe concept, one that offers a truly terrifying explanation for the cosmic silence, the Berserker probe. This concept flips the idea of exploration on its head, suggesting that not all self-replicating probes would be benevolent or even neutral. Imagine a von Neumann probe that, for whatever reason, a malfunction, a pre-programmed directive, or a shift in its original mission becomes hostile. Instead of exploring and replicating, its primary objective becomes the destruction of all intelligent life it encounters. It would land on a habitable world, consume its resources, build more destructive copies of itself, and then move on, leaving a trail of devastation in its wake. This Berserker scenario paints a grim picture of a galaxy scoured clean of intelligent life by relentless, automated weapons. Such probes would be the ultimate great filter, preventing any civilization from reaching a level of technological advancement where it could pose a threat to the Berserkers, or even just broadcast its presence too loudly. If a sufficiently powerful and efficient Berserker probe network was unleashed in the galaxy billions of years ago, it could have systematically wiped out every emerging civilization, leaving our own as a rare, temporary anomaly, or simply one that hasn't been discovered yet. The silence we hear in this terrifying context is the silence of a cosmic graveyard, meticulously maintained by unseen, unfeeling machines. This chilling hypothesis puts a horrifying spin on Fermi's question, suggesting that everyone is quiet because they were all destroyed, and we are just blissfully unaware of the cosmic predator lurking in the shadows. While the prospect of robotic berserkers or self-replicating probes silently sweeping the galaxy clean is terrifying, another approach to the Fermi paradox offers a far more philosophical and perhaps humbling explanation for the cosmic silence, the anthropic principle. This principle, at its core, suggests that the universe must have properties that allow for the existence of observers like us, because if it didn't, we wouldn't be here to observe it. Applied to the Fermi paradox, it implies that we observe a universe that is seemingly devoid of other intelligent life precisely because if it were teeming with easily detectable aliens, our own unique existence and the conditions that led to it might not have come to pass. To understand this, consider the incredibly fine-tuned nature of our universe. From the fundamental physical constants like the strength of gravity or the mass of an electron, to the initial conditions of the Big Bang, many parameters appear to be precisely calibrated for the emergence of complex structures, stars, planets, and ultimately life. If these constants were even slightly different, the universe might be a sterile void, incapable of forming atoms, or perhaps collapsing back on itself before life had a chance to begin. The anthropic principle argues that we can only exist in a universe where these conditions are just right. Now, extend this to the Fermi paradox. If the universe were indeed teeming with life and advanced civilizations, it would imply that the emergence of intelligent life is a commonplace event. But what if the very conditions that allow for intelligent life to develop and persist are so specific and rare that they effectively make our existence and our observation of this particular kind of universe statistically inevitable? We are here, therefore the conditions that led to our existence must be true. This perspective sidesteps the question of where is everyone by suggesting that the question itself is flawed. We are asking why we don't see something that, by definition of our existence, cannot be commonly seen. One way to interpret this is through the observer selection effect. Imagine a vast multiverse with an infinite number of universes, each with slightly different physical laws or initial conditions. In most of these universes, life never arises. In some, simple life might appear but never evolve into intelligence. Only in a very tiny subset of universes do the conditions allow for the emergence of conscious observers like us. We, as those observers, naturally find ourselves in one of these rare universes. So, the silence isn't a puzzle to be solved. It's simply a characteristic of the particular universe we inhabit, one that is conducive to our existence. If we were in a universe where intelligent life was common, our conditions might be different, or perhaps our unique evolutionary path would have been subsumed by others. However, the anthropic principle is often criticized as a cop-out, a form of circular reasoning that explains away the problem rather than solving it. Critics argue that it's a non-falsifiable statement, meaning there's no way to test it empirically. It simply states that things are the way they are because if they weren't, we wouldn't be here to notice. This can be seen as an intellectual surrender, an abandonment of the scientific search for concrete explanations. It doesn't tell us why these conditions are so fine-tuned or why intelligent life appears to be so rare. It merely states that if it were otherwise, we wouldn't be having this conversation. Some view it as a philosophical statement rather than a scientific hypothesis, akin to saying, the universe is the way it is because it is the way it is. Despite the criticisms, the anthropic principle offers a profound insight into our place in the cosmos. It forces us to acknowledge the sheer improbability of our existence, not just as a species, but as conscious observers capable of pondering such grand questions. It suggests that perhaps the conditions that allow for life, and especially for intelligent life, are so incredibly stringent that our very presence implies a universe that is, by its nature, sparsely populated with other observers. If the universe were teeming with diverse civilizations, it might mean the cosmic lottery for life is far easier to win than we assume, which would then make our specific set of just right circumstances less special and our unique path to intelligence less noteworthy. Therefore, the anthropic principle argues that the observed silence isn't a problem to be solved, but a fundamental characteristic of a universe capable of producing us. It's a humbling reminder that our perspective is inherently biased by our own existence, and that the universe we perceive is ultimately the one that permitted our perception to begin with. Even if we set aside the chilling possibilities of a dark forest or a great filter, and assume life is common and long-lived, the Fermi paradox still looms large because of the incredible potential for galactic colonization. If intelligent civilizations exist, and if they survive long enough, it seems almost inevitable that they would eventually expand beyond their home star system, eventually spreading throughout the entire galaxy. This idea leads us to examine various galactic colonization models, which predict how quickly a civilization could theoretically populate the Milky Way. And if these models are even remotely accurate, the persistent silence of the cosmos becomes even more deafening. One of the most influential thinkers on this topic was the brilliant physicist Freeman Dyson, who in 1960 proposed the concept of the Dyson sphere. While primarily a concept for energy harvesting, it also implicitly touched upon the idea of expansion. Later models, building on the concept of advanced technology, suggest that a civilization doesn't even need to travel at relativistic speeds to colonize the galaxy relatively quickly on astronomical timescales. Imagine a civilization that sends out colonization ships, each capable of establishing a self-sufficient colony at a new star system. Once a new colony is established, it could then, after a period of growth and development, launch its own set of colonization ships to further expand into neighboring systems. This process, often referred to as a percolation or diffusion model, suggests a relatively slow but steady wave of expansion. Consider a conservative estimate. If a civilization launches probes or colonization ships that travel at just 1% of the speed of light, and if each new colony takes, say, 1,000 years to become self-sufficient and launch its own next wave of ships, the entire Milky Way galaxy could be colonized in a matter of a few tens of millions of years. This might sound like a long time for us, but on a galactic timescale, it's a blink of an eye. The Milky Way is over 100,000 light-years across, and it's over 13 billion years old. 50 million years in that context is a tiny fraction of its history. Even if a civilization started its expansion just 1% of the way through the galaxy's history, they should have reached us by now. The fact that we see no evidence of this, no alien outposts, no ancient artifacts, no signs of advanced engineering on a galactic scale, is a profound discrepancy. The critical question then becomes, why do we see no signs of this? Why isn't the galaxy swarming with the evidence of ancient alien empires or even recent expansions? This absence forces us to critically examine the assumptions built into these colonization models. One major assumption is the continuous motivation for expansion. Do all advanced civilizations inherently seek to colonize every available star system? Perhaps not. A civilization might reach a point of technological maturity where it can perfectly sustain itself within its home system, or even on its home planet, with no need or desire for further physical expansion. Their growth might shift from material acquisition to intellectual or artistic pursuits, or perhaps they become so efficient at resource management that they require very little in terms of new territory. Why cross vast cosmic distances if you can have everything you need right where you are? Another critical assumption is the ability and willingness to maintain continuous long-term expansion. Colonization efforts would require immense resources, collective will, and constant technological innovation. What if the drive for expansion simply wanes over time? Or what if the challenges of managing an interstellar empire become too great, leading to fragmentation, collapse, or a deliberate scaling back of expansion efforts? Maintaining a single planetary civilization for millions of years is already a monumental challenge. Doing so across countless star systems introduces exponentially more points of failure. Communication delays across light years would make centralized control impossible, and local colonies might develop their own distinct cultures and priorities, potentially leading to a cessation of further expansion or even a withdrawal. Furthermore, these models often assume a continuous, unchecked growth model, an idea borrowed from biological expansion but perhaps not fully applicable to highly advanced technological civilizations. The very act of colonizing an entire galaxy could fundamentally change the colonizers. They might evolve into something entirely different, losing their original form, or perhaps their expansion takes a path we simply wouldn't recognize. Instead of physical colonization, perhaps they expand in informational or existential ways, transforming into entities that exist purely as data or energy, becoming undetectable to our crude methods of observation. The very process of becoming a galactic civilization might involve transcending the need for physical structures that we could detect. Finally, we must consider the first-comer advantage. If one civilization begins galactic colonization, even at a slow pace, they would likely reach every habitable system before any others. This would lead to a fill-up scenario where the galaxy is essentially claimed by the first successful colonizers, leaving no room for latecomers to expand or even emerge. The absence of any such pervasive presence suggests that perhaps no civilization has successfully completed this galactic fill-up, or if they did, they are so good at hiding their presence that we remain utterly unaware of their vast cosmic domain. The galaxy might be colonized, but in a way that is utterly beyond our current understanding and detection capabilities, leading to the profound silence that continues to confound us. Given the immense challenges of traditional communication across interstellar distances, and the often terrifying implications of making one's presence known, another fascinating, albeit highly speculative, solution to the Fermi paradox emerges from the cutting edge of physics: quantum communication. What if advanced alien civilizations aren't using radio waves or any form of electromagnetic radiation we can detect? What if they've harnessed the mind-bending principles of quantum mechanics to achieve instantaneous communication across vast cosmic distances, in a way that is utterly invisible and undetectable to our current technology? Quantum entanglement is one of the most bizarre and intriguing phenomena in the universe. Imagine two particles like photons or electrons that become entangled. Once entangled, they remain connected, no matter how far apart they are. If you measure the property of one entangled particle, say its spin, the other instantly assumes a correlated state, even if it's light years away. This spooky action at a distance, as Einstein called it, appears to violate the cosmic speed limit, suggesting information could be communicated faster than light. While the strict interpretation of quantum mechanics prevents direct, explicit information from being sent faster than light, and any message would still require a classical channel to interpret the quantum states, a highly advanced civilization might have found ways to exploit subtle quantum phenomena to encode and transmit information in ways we can barely even conceive. If aliens have mastered quantum communication, it immediately explains the cosmic silence from our perspective. They wouldn't need to send out energy-intensive radio signals that propagate at the speed of light, taking thousands of years to reach distant star systems. Their messages could travel instantly without any detectable signature in the electromagnetic spectrum, We could be listening with all our powerful radio telescopes and still hear nothing, simply because they are talking on a channel we don't even know exists, let alone how to tune into. Their conversations could be happening across entire galaxies, between civilizations millions of light years apart, all without leaving a trace for our classical physics-based instruments. Beyond the technical difficulty of detection, there's a strong logical reason why advanced civilizations might prefer quantum communication, security, and stealth. In a universe potentially governed by the dark forest principle, broadcasting one's presence with powerful, detectable radio signals would be an act of extreme recklessness. It's like shouting your address into a dangerous wilderness. Quantum communication, by its very nature, would be inherently private. It's not a broadcast, it's a direct point-to-point connection that wouldn't leak information into the wider cosmos. If a civilization could communicate instantly and secretly, why would they ever choose to risk their existence by emitting a detectable signal? The perceived silence of the cosmos in this context becomes a testament to the wisdom and advanced technology of those who choose to remain hidden, prioritizing their survival over open contact. Moreover, if they've achieved quantum communication, their entire technological paradigm might be fundamentally different from ours. They might not build visible megastructures or engage in energy-intensive interstellar travel as we imagine it. Their entire civilization might operate on principles that are so far beyond our current understanding of physics that their very presence would be invisible to us. Perhaps they exist as energy fields or consciousnesses interwoven with the quantum fabric of space itself, communicating through direct manipulation of reality at a fundamental level. This possibility pushes the boundaries of our imagination, suggesting that the problem isn't just about finding them, but about even recognizing them or their activities if we were to stumble upon them. Our current scientific understanding and technological capabilities are simply too primitive to perceive their true nature or their sophisticated methods of interaction with the universe. The silence, then, is not emptiness, but rather a reflection of our own technological and conceptual immaturity in the face of truly advanced alien life. Beyond the scientific searches and the cosmic filters, the Fermi Paradox also delves deep into the realms of human belief, challenging our understanding of existence and our place in the universe. It forces us to confront not just scientific unknowns, but also profound religious and philosophical questions. How do various faiths and worldviews grapple with the possibility of alien life, and what does the silence of the cosmos mean for them? For many religions, the concept of extraterrestrial life presents a complex theological challenge. If humanity was created in God's image, or if Earth is considered a unique creation, then the existence of other intelligent beings could potentially complicate core doctrines. Would alien beings also be considered God's children? Would they have their own messiahs, or would a single divine plan encompass all sentient life across the cosmos? Some faiths might find it easy to integrate the idea of alien life, viewing a vast, populated universe as a testament to the boundless creativity and power of their deity. God, in this view, is not limited to one pale blue dot. However, for others, particularly those with a strong anthropocentric focus, the thought of other intelligent species could undermine the perceived specialness of humanity and Earth's central role in the divine narrative. The silence in this context could be interpreted as confirmation of humanity's unique spiritual significance, a sign that we are indeed alone by divine design, placed here as the sole intelligent observers in a grand, empty stage. Conversely, if life were to be discovered, it would compel a re-evaluation of theological frameworks, perhaps leading to new interpretations of Scripture or a broadened understanding of the divine. This contrasts sharply with many secular views, which often approach the Fermi paradox with a sense of scientific wonder and intellectual curiosity. For secular thinkers, the absence of alien life is not a theological problem, but a scientific one that demands empirical investigation and logical deduction. The universe, in this perspective, is governed by natural laws, and the emergence of life, intelligence, and civilization is a direct consequence of those laws. If life is not abundant, then it suggests there are still fundamental aspects of these natural laws, or the conditions they create, that we do not fully understand. The search for extraterrestrial intelligence, therefore, becomes a quest for knowledge, a drive to complete our cosmic understanding rather than a spiritual journey. For many secular humanists, the very act of searching, of grappling with the profound silence, strengthens our appreciation for the preciousness and rarity of life on Earth, fostering a sense of shared responsibility for our planet and our future. Throughout history, thinkers have grappled with these questions. Figures like Carl Sagan, the renowned astronomer and science communicator, were deeply influenced by the philosophical implications of the Fermi Paradox. Sagan, a staunch advocate for the search for extraterrestrial intelligence, often spoke of the profound loneliness that would accompany the realization that humanity is truly alone in the universe. Yet he also emphasized the wonder and the moral imperative of seeking out other life, believing that contact could profoundly transform our understanding of ourselves. His work, like the novel Contact, explored not just the scientific aspects of first contact, but also the societal, religious, and philosophical reverberations it would create. Sagan envisioned a cosmos potentially teeming with life, and the silence was a puzzle to be solved through persistent, open-minded inquiry, not a sign of ultimate solitude. Similarly, the celebrated science fiction author Arthur C. Clarke, known for his 3 laws and his prophetic visions of technological advancement, also wrestled with these cosmic questions. While Clarke's work sometimes featured benevolent alien encounters, he also explored scenarios where humanity was alone or where alien intelligence was far beyond our comprehension. His famous short story, The Sentinel, which later inspired the film 2001: A Space Odyssey, delves into the discovery of an ancient alien artifact on the Moon, left by an intelligence that has long since transcended physical form. Clarke's vision often implied that the universe might contain intelligences so advanced they are indistinguishable from magic, or so ancient they have moved on to higher planes of existence, explaining their absence to our current methods of detection. His writings suggest that the ultimate answers to the Fermi Paradox might lie not in finding little green men, but in understanding deeper, more evolved forms of existence that challenge our very definitions of life and consciousness. The continued silence of the cosmos, then, is not just a scientific anomaly. It's a mirror reflecting our deepest hopes, fears, and beliefs about our place in the universe. It compels us to look inward as much as outward, forcing us to examine the very foundations of our worldview. Whether it strengthens faith in a unique creation, fuels the scientific drive for discovery, or inspires philosophical introspection, the Fermi Paradox profoundly shapes how we, as a species, perceive our cosmic destiny. The profound questions posed by the Fermi Paradox don't just occupy the minds of scientists and philosophers. They have deeply permeated popular culture, shaping how we imagine alien life and our place in the universe. Movies, books, and television shows have embraced the paradox, using its core tension to explore themes of contact, isolation, fear, and hope. This widespread engagement highlights how fiction often serves as a crucial lens through which the public grapples with complex scientific ideas, influencing our collective understanding and even our fears about what lies beyond Earth. One of the most iconic cinematic explorations of the Fermi Paradox is the 1997 film Contact, based on Carl Sagan's novel. The film directly embodies the dream of SETI, the search for extraterrestrial intelligence, chronicling the efforts of Dr. Ellie Arroway, who relentlessly listens for alien signals. When a clear mathematical message is finally received from the Vega star system, It shatters humanity's cosmic loneliness but simultaneously plunges the world into unprecedented scientific, religious, and political upheaval. The film masterfully portrays the challenges of deciphering an alien message, the global implications of first contact, and the deep-seated human desire for connection beyond our planet. Contact doesn't present the Fermi paradox as an absence, but rather as a profound silence that is eventually broken, exploring the very human reactions to such a momentous event. It showcases the hope and the fear that such a discovery would evoke, and how it would force humanity to confront its own divisions and aspirations. The film's enduring appeal lies in its optimistic yet realistic portrayal of what might happen if they finally called, offering a potential, if challenging, resolution to the paradox where intelligent life does exist and eventually reaches out. On a far darker and more unsettling note, Liu Cixin's groundbreaking science fiction novel, The Three-Body Problem, and its subsequent series offer perhaps the most chilling fictional exploration of the Fermi paradox through the dark forest theory. As we discussed earlier, this concept posits that the universe is a dangerous place where civilizations must remain silent and hidden, lest they be destroyed by more advanced hostile entities. The book meticulously details how one civilization's desperate cry for help across the cosmos inadvertently triggers a devastating interstellar conflict, revealing the brutal logic of the dark forest. Reading The Three-Body Problem fundamentally alters one's perception of the cosmic silence, transforming it from an enigma of absence into a terrifying testament to a galactic game of survival. It suggests that the reason we haven't heard from anyone is not because they don't exist, but because they are too terrified to speak, or because those who spoke were swiftly silenced. This narrative provides a powerful and dark counterpoint to the hopeful vision of contact, influencing a new generation of thinkers and solidifying the dark forest as a major, albeit terrifying, potential solution to Fermi's question. Television, too, has frequently delved into the mysteries surrounding alien life, with The X-Files standing out as a cultural touchstone. While not directly addressing the Fermi paradox by name, the show's core premise that advanced alien life has not only visited Earth but is actively conspiring with shadowy government forces to conceal its presence is a direct, albeit conspiratorial, answer to "Where is everyone?" Agents Mulder and Scully spend years pursuing the truth about extraterrestrial visitation, consistently rebuffed by official denials and elaborate cover-ups. The show taps into the public's fascination with secret knowledge and distrust of authority, suggesting that the silence we perceive is not an absence but a meticulously maintained deception. The X-Files popularized the idea that the invisible aliens are simply hidden from us, either by their own will or by a terrestrial conspiracy, making the apparent silence a deliberate construct rather than a natural phenomenon. The show's enduring popularity highlights a pervasive cultural belief that perhaps the answers to the Fermi paradox are already here, we just aren't allowed to know them. These and countless other works of fiction play a vital role in shaping public understanding and imagination regarding the Fermi paradox. They allow us to explore the scientific possibilities, from the optimistic discovery of new civilizations to the grim realities of cosmic filters. More importantly, they provide emotional and philosophical frameworks for grappling with the profound implications of being alone or not alone in the universe. Fiction allows us to simulate first contact scenarios, to experience the wonder, the fear, the scientific challenges, and the societal upheavals that such an event would entail. It keeps the questions alive, pushes the boundaries of our imagination, and encourages us to consider humanity's place in a cosmos that remains, for now, stubbornly silent. This ongoing cultural conversation ensures that the Fermi paradox remains an integral part of our collective consciousness, a mystery that continues to inspire both awe and existential reflection. Given all the profound questions and unsettling possibilities raised by the Fermi paradox, it could be easy to fall into despair or simply give up on the search. But humanity, at its core, is driven by curiosity and a relentless desire to explore. Rather than conceding to the cosmic silence, scientists and engineers are pushing the boundaries of what's possible, developing groundbreaking technologies that might just provide the definitive answer to Fermi's question within our lifetime. These ambitious initiatives are reshaping the search for extraterrestrial intelligence, moving us from passive listeners to active, imaginative explorers. One of the most ambitious and visionary projects currently underway is Breakthrough Starshot, a privately funded research and engineering program aimed at interstellar travel. Most of our previous discussions about interstellar travel highlighted the immense challenges of distance and time. Starshot offers a radical workaround. Instead of sending massive, slow spacecraft, it proposes sending tiny, wafer-thin probes, just a few grams in mass, equipped with cameras, sensors, and communication equipment. These nanocraft will be propelled by powerful, ground-based lasers, accelerating them to an astonishing 20% of the speed of light. At this incredible velocity, a journey to Alpha Centauri, the closest star system to our own and a prime candidate for exoplanets, could be completed in just 20 years. After arrival, these nanocraft would zip past, collecting data and sending it back to Earth using miniature lasers. This project is not without its monumental engineering challenges, from designing durable nanocraft that can survive the harsh interstellar environment to building and precisely aiming laser arrays powerful enough to achieve the necessary acceleration. However, if successful, it would mark a revolutionary leap in our ability to directly explore other star systems, offering the first opportunity to truly look for signs of life or even advanced civilizations up close rather than just listening from afar. Beyond ambitious interstellar missions, our ability to detect signs of life on distant exoplanets is also undergoing a transformative revolution thanks to next-generation telescopes. For decades, our exoplanet discoveries were primarily limited to inferring their existence through subtle wobbles in their host stars or tiny dips in starlight as planets passed in front of them. Now, with powerful new instruments like the James Webb Space Telescope, we are entering an era of direct atmospheric characterization. The James Webb Space Telescope, a marvel of engineering launched in 2021, is specifically designed to peer through the atmospheres of exoplanets, analyzing the light that passes through them to look for chemical signatures of life, known as biosignatures. Imagine being able to detect the presence of oxygen, methane, or even water vapor in the atmosphere of a planet hundreds of light years away. These gases, particularly in certain combinations, could be strong indicators of biological activity. While detecting direct signs of intelligent life remains a far-off goal for such telescopes, finding definitive evidence of simple, microbial life on another world would be a monumental discovery in itself, profoundly impacting our understanding of life's prevalence in the universe. It would suggest that the great filter of abiogenesis is not as insurmountable as some believe, shifting the focus of the paradox to later stages of evolution. Even with these incredible advancements, the search goes beyond looking for Earth-like planets or traditional biosignatures. Scientists are increasingly exploring the concept of technosignatures, any detectable indicators of technology used by an extraterrestrial civilization. This extends beyond radio signals to look for artificial light sources on exoplanets, industrial pollution in atmospheres, or even the heat signatures of large-scale infrastructure like Dyson Spheres. The Breakthrough Listen project, for example, is the most comprehensive search for alien techno-signatures to date, utilizing some of the world's most powerful radio telescopes to scan billions of radio channels across a vast section of the sky. It aims to broaden the search far beyond the traditional waterhole frequencies, recognizing that aliens might be broadcasting in unexpected ways or at unexpected frequencies. The sheer volume of data being collected requires sophisticated artificial intelligence and machine learning algorithms to sift through the noise and identify any potential patterns of intelligent origin. These future search initiatives and technological breakthroughs represent a new era in our quest for answers to the Fermi Paradox. They are not just about finding aliens, they are about understanding the fundamental laws of the cosmos, the limits of life, and our own technological capabilities. If Breakthrough Starshot successfully sends probes to Alpha Centauri, and if the James Webb Space Telescope discovers clear biosignatures in an exoplanetary atmosphere, the silence of the cosmos might finally be broken. Such discoveries would compel us to re-evaluate every current explanation for the Fermi Paradox, from the rare Earth hypothesis to the Great Filter. The possibility exists that simply by pushing the boundaries of our own scientific and engineering capabilities, we might, in our lifetime, be the ones to finally answer Fermi's profound question, revealing a universe that is either teeming with life or far more unique and solitary than we ever imagined. The ongoing quest to answer the Fermi Paradox, whether through advanced telescopes, interstellar probes, or listening for faint whispers from the cosmos, inevitably leads us to a profound ethical dilemma. Should we even be trying to make contact in the first place? While the desire to find alien life is deeply ingrained in human curiosity, the potential consequences of first contact are so immense and unpredictable that they have sparked heated debate among scientists, ethicists, and even governments. This isn't just about whether we can find them, but whether we should. One of the most vocal proponents of caution was the brilliant astrophysicist Stephen Hawking. Before his passing, Hawking repeatedly warned against actively broadcasting our presence into space. He famously cautioned that if aliens were to visit Earth, the outcome might be similar to when Columbus arrived in the Americas, which did not turn out well for the Native Americans. Hawking's analogy highlights the stark power imbalance that could exist between a technologically superior alien civilization and humanity. If an alien species has mastered interstellar travel and communication, their scientific and technological capabilities would likely be so far beyond our own that we would be utterly helpless against them. Their motives, while potentially benevolent, could also be entirely inscrutable or even hostile. They might view Earth with its abundant resources as a prime target for exploitation, or humanity as an obstacle to their expansion. Hawking believed that the safest strategy for now is to listen quietly and observe rather than drawing attention to ourselves. He advocated for a passive search, listening intently for signals but refraining from shouting into the cosmic void. His warnings resonated deeply, pushing the scientific community to seriously consider the potential risks associated with active SETI, or messaging extraterrestrial intelligence, where we deliberately transmit powerful signals aimed at specific star systems. The risks associated with making contact extend beyond outright hostile invasion. Even a seemingly benevolent encounter could lead to catastrophic cultural shock. Imagine what would happen if humanity suddenly discovered a civilization thousands or even millions of years more advanced than our own. Their knowledge of physics, engineering, medicine, and philosophy would dwarf ours. This immense disparity could lead to an existential crisis, rendering our science, religions, and social structures seemingly obsolete overnight. Would humanity lose its sense of purpose, its drive to explore and innovate, if all the answers were simply handed to us? Would our diverse cultures and belief systems fracture under the weight of such overwhelming external knowledge? The history of indigenous cultures encountering technologically advanced societies on Earth offers cautionary tales of cultural destruction, loss of identity, and societal collapse. The psychological and sociological impact on humanity could be profound, leaving us feeling insignificant and overwhelmed. Even if aliens offered aid or technology, it could inadvertently stunt our own development, making us dependent or fundamentally altering the very path of human evolution. Another significant risk is the potential for biological contamination. If a civilization were to encounter another, there's always the risk of transferring pathogens against which one species has no immunity. While this risk is likely much lower for interstellar contact than for interplanetary contamination due to the vast distances and harsh conditions of space, it's a concern that has been raised particularly in the context of probes returning from other planets. A more subtle form of contamination could be informational or ideological, where alien philosophies or social structures could destabilize our own, leading to unforeseen consequences. Despite these grave warnings, many argue that the potential rewards of contact far outweigh the risks. The opportunity to share knowledge with an advanced civilization could lead to unprecedented breakthroughs in science, technology, medicine, and our understanding of the universe. Imagine access to technologies that could solve our energy crises, cure diseases, reverse climate change, or even unlock the secrets of faster-than-light travel. Such an exchange could accelerate human progress by thousands, if not millions of years. We might learn about new forms of energy, advanced materials, or even entirely new ways of thinking and organizing society that could help us overcome our own self-destructive tendencies and existential threats. Shared knowledge could be the key to humanity's long-term survival and flourishing. Furthermore, contact could provide answers to some of humanity's deepest philosophical questions. Are we alone? What is the meaning of life? What is our place in the cosmos? An encounter with extraterrestrial intelligence could provide a mirror, allowing us to see ourselves and our challenges from a cosmic perspective. It could foster a sense of universal unity, transcending our petty terrestrial divisions and uniting humanity in a shared cosmic destiny. The wonder and inspiration derived from knowing we are not alone could ignite a new era of global cooperation and exploration, pushing us to achieve greater heights than ever before imagined. For many, the very thought of dialogue with another intelligent species, the exchange of ideas and perspectives across light years, represents the ultimate adventure and the most profound form of discovery. This debate between caution and curiosity, between the fear of the unknown and the hope for enlightenment, remains at the heart of our continued search for answers to the Fermi Paradox. As we draw towards the conclusion of our exploration into the Fermi Paradox, it's clear there's no single, universally accepted answer to Fermi's profound question. The truth, if we ever discover it, might be a complex tapestry woven from several of the solutions we've discussed, or perhaps something entirely unforeseen. But before we wrap up, let's briefly touch upon a few more lesser-known, yet equally intriguing alternative solutions that stretch the boundaries of our imagination. These theories, while perhaps more speculative, remind us of the vastness of the unknown and the countless possibilities that could explain the cosmic silence. One such idea suggests that alien civilizations might be in a state of hibernation or deep sleep. Imagine an advanced species that has reached the pinnacle of its technological and social evolution. They might realize that the most efficient way to survive the vast timescales of cosmic change and to conserve resources is to enter a long period of dormancy. Perhaps they anticipate a future cosmic event like the eventual burnout of their star or a period of intense galactic radiation, and choose to collective power down, only to awaken millions of years later when conditions are more favorable. They might even hibernate to await a more opportune moment for galactic exploration, perhaps when the universe is older and energy sources are more efficiently harnessed, or when the expansion of the universe makes certain forms of travel more viable. From our perspective, these hibernating civilizations would be utterly invisible. Their cities would be dark, their signals silent, their megastructures, if any, powered down and dormant. Detecting such a civilization would require an understanding of their hibernation cycles and the ability to detect incredibly faint, non-broadcast technosignatures or historical markers, which would be incredibly challenging. Another alternative solution posits that we might be living in a cosmic desert. While the statistics of the Drake equation might suggest a teeming universe, perhaps life, and especially intelligent life, is incredibly rare even if the conditions are right. This isn't quite the same as the rare Earth hypothesis, which focuses on geological and astrophysical conditions. Instead, the cosmic desert theory suggests that there might be something even more fundamental restricting the emergence or longevity of intelligent civilizations. Perhaps the evolutionary pathways leading to intelligence are much more complex and fragile than we assume, or the probability of any given intelligent civilization surviving long enough to make contact is exceedingly low due to factors we don't yet comprehend. It could be that our corner of the galaxy, the Milky Way, is simply a sparsely populated region, and the nearest civilizations are so unimaginably far away that their signals haven't reached us yet, or their probes are still millions of years from our vicinity. In this scenario, the silence is not a sign of fear or a hidden agenda, but simply the vast, lonely reality of space. The universe is big, and even if life is out there, it might be so thinly spread that encounters are virtually impossible. Finally, one of the most intellectually compelling, yet challenging, explanations is that alien life might simply be too alien for us to recognize. We've discussed non-carbon-based life, but what if their existence goes beyond even our most imaginative scientific theories? What if alien intelligence doesn't reside in biological forms at all, but as distributed networks of consciousness within planetary systems, or as sentient energy fields that occupy regions of space? Their communication might be through gravitational anomalies or subtle manipulations of spacetime itself. Their civilizations might not build structures, generate heat, or emit electromagnetic radiation in ways we could detect. Their goals, their motivations, their very concept of existence could be so fundamentally different from our own that we wouldn't even perceive them as life, let alone as intelligent beings. It's like a fish trying to comprehend the existence of an entire city of humans. The fish simply lacks the sensory and cognitive framework to even register such a thing. Our human-centric models of life and intelligence might be a profound limitation, blinding us to the vast diversity of existence that the universe might hold. We might have already detected them but dismissed the evidence as natural phenomena or simply as glitches in our data because we couldn't conceive of what we were seeing. These alternative solutions underscore the humbling truth about the Fermi Paradox. It forces us to confront the limits of our own knowledge and perception. The universe is not obligated to conform to our expectations or our current scientific understanding. The answers might lie in physics we haven't discovered, in forms of life we can't imagine, or in histories so vast and ancient they dwarf our own. The persistent silence of the cosmos, therefore, remains one of the most tantalizing and profound mysteries of our time. It compels us to keep searching, to keep listening, and perhaps most importantly, to keep questioning our own assumptions about life, intelligence, and the very nature of reality. What do you think the answer is? Could it be a combination of these theories or something entirely new? What possibility resonates most with you and why? The Fermi Paradox is a grand cosmic puzzle, and every one of us, as curious inhabitants of this pale blue dot, has a unique perspective to bring to the table. As our journey through the many facets of the Fermi Paradox concludes, it's clear that the universe holds its secrets close. We've explored everything from the overwhelming statistical likelihood of alien life to the terrifying implications of a dark forest, the unique conditions of a rare Earth, and the possibility that aliens might simply be too advanced or too hidden for us to detect. We've even considered the mind-bending idea that our entire reality might be a simulation, or that life could arise from chemistries completely alien to our own. Each theory offers a compelling, yet ultimately unproven, explanation for the profound silence that surrounds us. The Fermi Paradox remains one of the most enduring and captivating mysteries in all of science. It's a question that doesn't just challenge our understanding of the cosmos. It challenges our very perception of reality, our place in the universe, and our potential future. This paradox doesn't have a simple answer, and perhaps it never will. The truth might be a complex tapestry woven from several of the solutions we've discussed, or perhaps something entirely unforeseen, lying just beyond the current reach of our scientific instruments and our human imagination. The universe is under no obligation to make sense to us, nor is it required to conform to our expectations of how life, intelligence, or civilization should unfold. We are still infants in the cosmic scheme of things, only just beginning to truly grasp the immense scale and complexity of the universe we inhabit. However, the enduring mystery of the Fermi paradox is not a sign of failure or a reason for despair. Quite the opposite, in fact. It serves as an incredibly powerful engine for scientific discovery, pushing the boundaries of our knowledge and inspiring innovation across countless fields. The very act of wrestling with Fermi's question has driven humanity to develop revolutionary technologies. Our relentless search for exoplanets, spurred by the need to understand where life might arise, has led to incredible new telescopes and observation techniques, revealing a galaxy teeming with billions of worlds that were previously invisible to us. The quest to understand the origins of life, to determine if abiogenesis is common or rare, fuels groundbreaking research in biology, chemistry, and geology, helping us decode the very essence of existence. Even the theoretical physics behind concepts like warp drives or quantum communication, while still speculative, is propelled forward by our desire to bridge the vast cosmic distances and understand the fundamental laws of the universe that might enable interstellar travel or communication. The paradox forces us to ask deep questions not just about others, but about ourselves, our longevity, our wisdom, and our future. It forces us to confront our own existential risks and consider the choices we make today that might determine whether humanity becomes a fleeting flicker in the cosmic night or a long-lived interstellar civilization. Beyond the scientific advancements, the Fermi paradox also ignites our imagination and fosters a sense of wonder that is crucial for our collective human spirit. It inspires countless works of science fiction, art, and philosophy, providing a canvas upon which we can explore every conceivable possibility, from utopian galactic empires to terrifying cosmic predators. It keeps us looking up at the night sky, not just with scientific curiosity, but with a profound sense of awe and a nagging question: is anyone out there looking back? This shared cosmic mystery unites us, transcending borders and cultures, in a universal quest for understanding. Whether we are truly alone or merely isolated by unimaginable distances and incomprehensible forms of life, the journey of searching enriches our lives and expands our cosmic perspective. So, as we conclude this deep dive into the Fermi paradox, the question remains open, beckoning you to join the conversation. What's your theory? After exploring all these possibilities, what do you believe is the most likely explanation for the cosmic silence? Is the great filter ahead of us or behind? Are aliens simply too far away, too alien, or too wise to make contact? Do you believe we are truly alone, or is the universe teeming with hidden life? Share your thoughts and theories in the comments section below. If this exploration into the mysteries of the universe ignited your imagination and you want to delve deeper into more cosmic enigmas, remember to like this video, subscribe to our channel for more content, and hit that notification bell so you don't miss our next journey into the unknown. Your engagement helps us continue to explore the biggest questions facing humanity.